Good morning, everyone. My name is Sylvain Lézé from Imperial College, and this is a new episode of the Turbulence at the Exascale podcast. As you know, the aim of the podcast is to gather the view of the community regarding exascale computing for turbulence and what are the challenges and opportunity associated with exascale computing for turbulence research. So this podcast is part of the UK ExCALIBUR initiative. The aim of the ExCALIBUR initiative is to harness the power of exascale computing in the UK by developing and redesigning simulation code. And I work at Imperial College in the Department of Aeronautics. I'm also the lead of the UK Turbulence Consortium. The Turbulence UK Consortium is a group of academics focusing on using high-performance computing to investigate fundamental aspects of turbulence problem. And this podcast is also linked to the UK Turbulence Consortium. I'd like to say finally that the ExCALIBUR project is a program led by the Met Office, by the UK Atomic Energy Authority, and by the UK Research and Innovation. And today my guest is Neil Ashton, who is Principal CFD Specialist Solution Architect at Amazon Web Services. And I think he joined Amazon in February this year. He was previously a senior researcher at the University of Oxford. He's going to talk about that very soon. So good morning, Neil, and welcome to the podcast. It's very nice
Thank
to
you.
be around. So, well, let's crack on. So can you tell us more about yourself, where you're from, where you have studied, and any previous position?
Yeah, sure. Well, thanks for having me on to start with. So yeah, I suppose maybe we have quite a similar background in some ways of a kind of turbulence modeling start in life. So I did my undergrad and then PhD at Manchester University, which was just kind of a full-on turbulence modeling K-epsilon kind of place, which I think at the time maybe I didn't realize. In my undergrad days with having, Brian Launder and people like that teach you. And it was only later on you're like, oh, actually, okay, he actually did quite a lot, but when you're a third year undergrad, you don't really think about that. So yeah, and all the UMIST days and stuff like that. So it was only later on in my life that I realized it was quite a cool place to be. And I suppose what sums up my kind of previous career has been this jumping between, I suppose, one foot in academia and one foot in industry. I like the appeal of the deep thinking and kind of being curious in the academic sense, but then I like the applying it in industry and the kind of speed that things happen. So as you said, I had a bit of a background working in Formula One before, which kind of, probably like a lot of engineers was a bit of a passion to study engineering in the first place. That's how I got into CFD. I kind of did I think a 4th-year project or something like that of doing a car. And yeah, that kind of spurred me on. And I suppose like a lot of people, you jump out of your PhD thinking, God, I definitely don't want to be in academia. I'm sick of this. I just want to go and get a job somewhere, and then quickly realized actually it was quite nice having that freedom. So went back to Manchester for a postdoc for a while, and yeah, I suppose fast forward to now, and I kind of gone to a place that I feel actually is, again, somewhere in between at Amazon Web Services, where there's this very kind of day one feel of kind of like you had when you start your PhD, but obviously in a pretty big company. So yeah, I suppose that's my very brief summary of how I've got here.
Thank you. And can you tell us how you became interested in high performance computing in computational fluid dynamics?
Yeah, so I think again it was the Formula One thing that I had this dream of wanting to work with Formula One, and probably wasn't really sure what I could do, but I was always a bit of a geek. Interested in kind of computers from an early age. And so I think when I started, I think it was with Alistair Revel, he helped me be like 4th-year student, and being able to combine that kind of IT programming, playing with a computer, and the engineering side, I kind of got hooked onto the CFD. And well, as you know, HPC and CFD are kind of closely linked. So I ended up just trying to get my hands on as much compute as possible from the very beginning.
Ah, very good. So you've joined Amazon Web Service this year, earlier this year, I think February or something like this. So what's the best thing about your job and about working at Amazon Web Services?
Yeah, I think it's probably the kind of freedom that you get to just take what you think is right. You know, it's a very, people are hired at Amazon because of who you are. You know, it's a cultural fit essentially. And then, you know, if they think that you have met the bar and you fit the culture, then there's a lot of freedom given to you to go and do what you think's right. And so, of course, with something like CFD, that is this, you know, really big and still growing space, it's just fun to be able to one day speak with a company in Australia about some motorsport and then be working with NASA on the other side. And yeah, it's pretty fun, basically. Doesn't really feel like a job, which is hopefully a good thing. Very
good. So obviously, I mean, this is the new, I will say, new trend, not that new, but it seems that using the cloud, I will say, in CFD is fairly new, I would say. So can you tell us more maybe about Amazon Web Service, I will say, business model for CFD, and also what you are offering for academics and what you are offering for people like me who may want to use Amazon to run some simulations?
Yeah, so I think the big one, I mean, it's a pay-as-you-go model, essentially. That's at the heart, you know, computing in a pay-as-you-go model. So there's no kind of upfront need to spec some sort of machine. You just turn up and decide what you want to do that day. So for me, it's, I think what I like, because I was using it before I joined, is if I want to be creating a really big mesh, I used to have a workstation that I think over a few years I'd built up to have like 260 gigs of RAM or something like that. But it was getting old. And it was when I looked at the cost of getting a new workstation, you know, with that much RAM, and I thought, well, I don't need it all the time. I just occasionally need it for something really big. And then suddenly this idea that you could go on and spin up a, you know, couple of terabyte RAM machine just for that few hours when I needed it. It was like a kid in the candy store, you know, sort of thing that you can just be spinning up and down. And so I suppose that is one of the things that is quite appealing from a research angle, is especially if you start going into GPUs. And I remember we would be trying to get hold of one, and maybe at that time, you know, still it's quite rare to get one if your university doesn't have access to one, and then you have to kind of write this proposal maybe to try and get access to some machine. So I think now this ability just to spin up and down pretty much any hardware is quite appealing from a testing point of view, development point of view.
So, I mean, at Amazon, you are offering hardware, but I guess you're also offering some expertise, right?
Yeah, I mean, what I should say as well is the interesting is people tend to start off with their workflow in mind. So they're a CFD person. And so they're naturally thinking, okay, it's just about the infrastructure. So what we call EC2. So you can spin up a GPU or CPU, but then you quickly realize once you get in there that actually AWS is composed of, you know, more than 170 different services, from like machine learning to databases, you know, so you slowly start to think, oh, maybe I could actually link that database because I'm running a lot of jobs. So maybe I should hook up that database, and and then maybe I see some of these machine learning services. So maybe I could hook up that. So it ends up going from just an infrastructure to a lot more than that, I suppose. So that's the journey, the interesting journey that people tend to find as they open up more and more possibilities, which I have to say I'm still nowhere near explored enough.
Very good. So what's your role exactly at Amazon? What do you do on a daily basis?
Yeah, so I suppose as a CFD specialist, I sit within the broader high performance computing team. Mm-hmm. And so I lead the kind of worldwide effort on the CFD area. So that's on one side would be speaking with customers who, want to explore moving to AWS. So helping them discuss about what they want to do, either deeply about the MPI compilers or just the high level needs of CFD. That's kind of, I suppose, the external facing side, and doing things like this, just kind of still the academic one-to-many sort of activities. And then the other side is actually feeding all that back to our service teams to try and help to develop the next services and the next hardware. So there's, I suppose, two sides of the role like that.
Great, fantastic. It's very interesting job, I guess. So what are the challenges associated, with the, I will say, the cloud model at Amazon, in terms of increasing the hardware capabilities, increasing the expertise and things like this?
I think probably the biggest challenge is just awareness. It's, as you just rightly said, that probably if you were to go and ask a lot of CFD people, what you know about the cloud, they would kind of, depending on who you speak to, they would range from knowing that they can use it on their phone to maybe having tried it at some point. But I'd say we're still in the very early days. So I think the biggest challenge is probably just a perception and awareness thing. And most common reaction I have is people go, oh, okay, so it's not actually that different then. When they actually see the Linux terminal or the cluster come up, it's usually a moment when people realize, okay, it's not very different. But initially they thought it was somehow this very complex thing. So yeah, I'd say the main challenge is just awareness, and I suppose a little bit of training in a way, kind of cloud, because I suppose you're also then aware of more of like the network side of things as well, or you can be, which maybe traditionally you've not been because you've had somebody else to do that. So sometimes what people say is cloud brings the technology closer to the business. So as an end user, you have a more easy way of setting up an entire infrastructure yourself, where I suppose with the older model, you would probably need more IT support to do that, because you would have to be, installing hard drives or connecting stuff up, where on a cloud model, it's more based in a kind of a console environment. So yeah, awareness and training probably are the two ones I'd say.
And if I'm an academic and I want to start looking into using Amazon Cloud for my simulation, what's the best way forward? Is there any training resources, tutorials available?
Yeah, so probably the starting one, and it's something that we're developing all the time. There's a website called hpcworkshops.com, and basically it's a set of workshops that's been done going through the kind of classic things that you might want to do on AWS in terms of HPC. So how you would set up a cluster, or how you would do like a containerized workflow, how you do remote visualization, all that kind of stuff. So probably that's one. And then if you go onto that page, it's a bit like watching YouTube. You can just suddenly start opening up so many avenues, and you start to explore all the kind of underlying services. So yeah, and I suppose some of the webinars, I mean, I've tried to do a few to kind of show the very practical nature of it, like how you would actually do it rather than just following through a tutorial. So probably a combination of those two, hopefully.
Very good. And in terms of hardware, any type of hardware is available, or it's more centered around GPUs, or you're also offering a wide range of
so I think the last time I looked, I think there were more than 400 instances available. So, and we say, it's true to say that we have the broadest and the deepest set. So if you think there's AMD, so AMD EPICs, there's Intel of a range all the way up to kind of Cascade Lake, where there's the Graviton 2, so the ARM processors that have been custom designed silicon by AWS. And then there's NVIDIA GPUs and AMD GPUs. So yeah, you basically got your pick. That's the kind of whole thing. it's very rare for you to find a scenario when you don't find what you're looking for in terms of memory to CPU. Yeah, it's all there basically.
Very, very good. And might be a tricky question that I'm wondering in terms of size. How big can you go? Let's say if you were to do some comparison with, for example, the UK supercomputing facility Archer. So it's only CPU based, I know that, but can you do similar simulation on the Amazon cloud that you can do on Archer, for example? So I'm talking about using, I don't know, maybe 8,000 or 16,000 cores.
Yeah. Oh yeah, yeah, definitely. I mean, and we have people routinely doing that. So that kind of scales available, and you know, we're adding infrastructure every single day. I think what's also very interesting is if you think the cloud model as well is we have something at, I think the time of recording, 24 regions. So each region being a kind of geographical area where we have resources. And then within that, we have availability zones, which are kind of localized, isolated, you know, a meaningful distance apart, power, network, everything. And then inside that, we have, you know, data centers. And if you look inside those, we have, like I said, you know, more than 400 instances. So I think what's really interesting, if you look at some of it, is I think we had an example a couple of weeks ago where we had a company do a seismic workload that was, I think, just over 1 million vCPUs. So what, about 500,000 CPUs on Spot, which is our unused capacity model. So, you know, there is a lot of capacity out there. Yeah, it's growing all the time.
Fantastic. So there is no risk that if everyone wants to use the Amazon cloud at the same time, you will be fine.
Yeah, I mean, that's the thing as well, because it's a global infrastructure. You know, there is so much planning for kind of demand that, you know, we'd like to think that we can service that demand when people need it. So
just one last question, because I'm very curious. So if tomorrow I want to run a simulation on Amazon cloud, so I'm based in the UK, does it mean that the instances that I'm going to use are based in the UK, or they can be anywhere in the world? Because you mentioned like 24 local areas, right? So how this is?
So that's designed so, you know, if you think about it, so that, yeah, there's 24 regions, and that is essentially, if you boil down to them, data centers. And that's to mean that if you are in London, you could run in our London region.
Okay.
So, and you could, you know, provision resources there. And some people need that for latency reasons. You know, they need to be very close. Like if you're doing remote visualization, you want to be as close to the machine as possible. But of course, if you're in Virginia, you could use the Virginia, or if you're in Sydney, you could use the Sydney region, or Bahrain, you know, etc. So yeah, that's the idea. And also some of it is for data sovereignty. Some people want it to be in the US, some people want it to be in Europe, etc. So it's designed for those needs.
Fantastic. So I know you are working a lot with, well, you mentioned Formula One companies, but I was wondering if you could tell us about a recent example or case study from a company who is using your services for their research. I know maybe you cannot say too much about the research, but it would be good for us to hear about a nice story.
Yeah, so I mean, from a kind of research point of view, and maybe it's a company and some names that people may know in this kind of turbulence modeling community, which is the guys down in Bristol at Xenotech, Jamil and Mike Turner. So we've been doing a lot of work with them recently on testing their code ZCFD on some of our A100, NVIDIA A100 GPUs, which is the P4D instance. So that's been really interesting, because what we were basically doing, and it's actually should be published soon, is trying to see this question of CPUs versus GPUs. And when I looked through the literature, I realized there was some attempt to compare, but it's quite hotly debated. You know, I've been to many conferences where some people really hate it when people claim that GPUs are 100 times faster, and they always complain, oh, well, it wasn't a fair test. And it always felt that also the cost wasn't really considered, because the one thing I've learned about being at AWS is that very few people want pure performance. Most people want price performance. Doesn't matter whether you're in academia or in, it's price. It's never performance at any cost. So you really need to check. And so that was interesting in this work, because we were able to test, different CPUs, so ARM and x86, and different generations of the NVIDIA GPUs. And the end result being that actually the A100 was about 2 to 3 times faster than the CPUs, and the CPUs could never get as fast. They'd reached the limit of scaling basically by around 3,000 cores. It was a 150 million cell aircraft case, and the GPUs was about 2 or 3 times faster in terms of absolute runtime, thing. But interestingly, on AWS, it was about half the price. And that's just all with public pricing. So you can just go on a website to simply the number of hours a simulation runs by the number of them. And that was really interesting, because I had never seen that put so clearly in that kind of performance versus price context. In the past, I'd seen people say, well, if I was to buy a GPU, it would cost this much. Mm-hmm. But that doesn't really account for putting it in a physical place, the cooling, the networking, all the rest of it. So that was one piece of research that I thought was quite interesting, actually, and I'm hoping it will spur on maybe a few of the bigger codes, to accelerate moving on to GPUs, because it was quite a good result from my perspective, from a customer point of view. Twice as fast, half the price. I mean, can't really complain.
That's the dream.
Yeah.
Very good. This podcast is about exascale computing. So I have a question for you. So we are talking a lot about transition to exascale, and hopefully the UK is going to invest in an exascale computer in the next few years. So I have a simple question for you. Will exascale computing be possible on Amazon, or is it already possible in a sense? Like if you were to use everything that's available, or what's your plan on that?
Yeah, probably if you were to sum up, all the compute in all the regions, all the, availability zones, then it could very well be more. I suppose that's not the classic exascale machine, but in terms of available, compute. But I suppose the one thing I always say is, at the moment, and this is where I suppose we have to be quite focused on what customers are asking us, very few people are asking for that at the moment, in the sense that, all the companies, whether it's research, are coming to us, typically saying, I have a case, I need to run 500 cores or 1,000 cores. As you're aware, it's, very few codes can even scale up to that far. So I suppose at the moment, we have to be focused on what people are asking us to be. But I think where AWS plays potentially a valuable role in the exascale is just the sheer amount of compute we have, and the kind of data center design and the scale that we have, that I think is probably, and even though this is not my particular area, is probably something where we could play a part in helping to inform, that sort of thing, just because of the sheer scale of what we had. And I think also, if you look at, or at least in my opinion, if you look at kind of exascale computing, I would say it's as much also about, from a CFD perspective, the visualization and the meshing, as it is about the solve. And so actually having not only, many GPUs or CPUs to run, but also the right stuff to build massive meshes or remote visualization of the solution on the fly is also quite important. So I suppose that's where a cloud model, where the kind of data is there, and we have individual customers using more than exabyte of data, individual customers. So, there's a lot of data availability as well, which is obviously linked to exascale. So yeah, it's a very interesting question, and I'm sure AWS would like to play its part and, yeah, I need to get into it more myself, to be honest. I need to catch up with what the latest work is in that area.
Right, thank you very much. So, I mean, you touched this a little bit when you said that, well, most of the flow solvers are probably not GPU ready yet, but I was wondering, what do you think about the readiness of the community, and especially the turbulence community, for the transition to exascale computing, or at least for the transition to GPUs and to accelerator technology?
Yeah, so I mean, it seems to be that the challenge is still, I remember my time, and I still have a, visiting position at Oxford, is the software support, so I think that's always been the challenge, is that for students doing research, they may be looking at the latest, War Model ES or DNS, but how many of them know how to write a good code, and how many of them have the support to do that? So I think things like the research software kind of community is really important, and I think probably most codes are not ready for exascale just because the knowledge and the training to build the codes is not there, probably because the staff aren't there as well. I mean, I know that community is growing, but I'd say that's probably the limiting at the moment. I'd say the kind of software support.
Very good. And I would like to have your personal opinion on that. So if I have a CPU-based flow solver, would you suggest I move to a GPU solver, or do you think that there will still always be an alternative? So like the new Fugaku system in Japan is CPU-based only. So there is an argument to say, well, should I really move to GPUs, or shall I stick to CPUs? I mean, you gave a good example with Xenotech, where it's 2 or 3 times faster and half the price. So I guess I can anticipate your question, but I was wondering what you have to say about that.
Well, I think, and I think this is where people like Mike Giles has done some work, and Gihan in Warwick now. That kind of idea of designing a code that can be ready for future, because we don't know, do we really? I mean, I'd like to think at AWS we probably have a little bit of a on the pulse of future hardware, but you never know, because it really does depend. What if we all move more to explicit codes, and then the idea of kind of memory stuff isn't as important, where at the moment everything's kind of memory bandwidth bound, so it pushes down a certain direction. So if possible, I think the idea of designing a code to be agnostic is actually the better approach than picking one or the other.
Good.
Easier said than done, of course.
Yes. So if there is one thing about high performance computing that you could change, what would that be? That's a tricky question.
Yeah, I think making it more accessible, I suppose, was all my thing. And now I know this sounds like a plug for the cloud, but I do mean it, that it always felt as if the top institutions had access, or easier access to the biggest facilities. They have the track record, they have the thing. So if you wanted to get time on a big machine, then you could kind of, do it. And I always felt sometimes that sometimes left behind the smaller universities, or the quote unquote less prestigious, although that's probably not true, access. So I suppose making it more available is actually quite important. And I genuinely believe that is one advantage of the cloud, that it does actually make it easier for people to access it. You still need the training, you still need the kind of expertise to teach these people how to do it. But I think if I could change one thing, it would be the easier access, because I've seen so many people even now still buy really big workstations and buy some stupidly large amounts of RAM and RAID like hard drives, because they're not willing or they're not able to move on to a kind of a HPC system. So yeah, that's probably the one thing I'd change.
Very good. Another maybe related question is, what do you think is going to be the landscape for CFD in 10, 20 years? Are we still going to be debating between CPU, GPUs, or you think we are going to be, everyone will be on the cloud, or where do you think?
Yeah, so it's difficult to say. I mean, I think it's for sure that people, will be moving to the cloud. I think that's just a general push, and that's broader than CFD. That's from a engineering, from an IT perspective, from just a global kind of company, universities as well. But leaving that aside, on the actual thing, I suppose the bit that I'm interested in is whether we ever make LES, and I mean wall-resolved LES, affordable. Because if you look at the current costs now, it is very expensive. So I feel like we either need some real breakthrough in something that can significantly reduce the time, and I don't mean just in a hardware sense. Either some interesting stuff around like parallel in time, or some sort of more novel thing, or, and I'm kind of leaning towards this more actually, is the increased use of deep learning models. Because if you look at the pace of development in that area, the number of papers published, the number of demonstrations, and the cost for it, and the fact that you can train it on physical data as well, I'm almost wondering whether we'll actually move down that way, rather than seeing the day when, everyone predicted DNS will be a daily occurrence. I don't know, there's something just makes me think that it's the machine learning stuff is going to push us in a different direction. But I want to listen back to this podcast in 10 years time and see how right or wrong.
Yeah, let's have this chat again in 10 years or see where we are. I think
we'll probably still be doing RANs, I'm sure, just on a slightly bigger meshes.
Very good, very good. Thank you very much. I have a couple of more questions. One question is, you're organizing some automotive CFD prediction workshop, and maybe people who are going to listen to this podcast are not familiar with this, but I think it's a very interesting initiative. And so if you can tell us more about that, I think that would be very valuable.
Yeah, sure. So it basically started because I've been quite involved with the high lift prediction workshops and the acoustic workshops, which is run by the AIAA, in coordination, with NASA and Boeing and others. And I got quite involved in the last one, and I really thought it would be great if there was something for the automotive community, because there hadn't really been. And the Drive Air model came out, which was this open source car, and everybody started to run and publish, but people weren't using exactly the same meshes. The geometry variations was there, and there was a lot of still mystery around what was the actual end conclusions. So I decided to create it, and we held it in Oxford last year for people to basically run a couple of test cases with the same grids. We had really good participation from software vendors, from the car companies, and such that now we have a second one, which is going to be this summer. So I think August 2021, where it would be a similar model, but we've got even better experimental data, more kind of rigorous organizing. And so, yeah, I'm hoping people will join and test their new turbulence models and methods against, the automotive companies and the software companies. So, yeah, and I should say as well, there's a similar effort going on now, which people may be interested in, with the 4th high lift prediction workshop, and I'm helping to lead the hybrid RANs bit. And interestingly, all the previous workshops have pretty much been RANs based. And it's been clear that even though there's been a tightening of the results, there's never been a clear path to correlation, perfect correlation. And so this year is the first year when there's a real sizable number of people running warm mold LES and hybrid RANs LES, really big simulations of these full aircraft. So that's also in, I think, July 2021. So that should be also an interesting one to watch out for.
Thank you very much. Thank you very much. I have one final question. If you can give us a name of someone we should invite to talk about, high performance computing and turbulence, maybe with a focus on the UK landscape, that would be very valuable for us.
Well, I know that he doesn't do things in this area as much these days, but I think Mike Giles would probably be an interesting one to get in to get some of the historical things of how things developed, or maybe someone like Wes Moore, who's kind of taken over some of his stuff and was also my boss when I was at Oxford for some time. So yeah, probably one of those two I think would be a good idea.
Mike is on my list. He was recommended by Jihan as well. So
okay.
I will definitely on my list for 2021.
Yeah.
Well, Niels, thank you very much for your time and for your inputs. I think it was very valuable, and I hope for those who are not aware of cloud possibilities, then now you know a little bit more about what can be done with Amazon service. I wish you all the best for your future endeavors. I mean, I guess you are very busy. I can see that. So best of luck for all your initiatives. For the podcast, you can find all the links on the UK Turbulence Consortium website. So it's ukturbulence.co.uk, and the podcast will be made available on YouTube and on SoundCloud. I will tweet about that as well. So it will be very easy to find the links. Thank you very much, Neil.
Great, thank you. Really enjoyed it. Good to speak to you.
Hopefully we'll see everyone for the next episode. Thank you.